guys, my name is Sandip, and we are on our chapter that is electricity and circuit, right? Good. So we already have covered two sessions on that, and we know that in first session, if you do remember, we have started talking about the charges which are at rest, static, right? Static is the word I told you, which is very important for us. Then we also talked in that session about the electrons, protons, neutrons, what are the different charges on the earths, what are the masses of those different things, right? So just we also saw that how the current flows. When we say current flows, which particles do flow, whether those are electrons or protons, right? Electrons do flow, not protons, right? So negative charges flow, I can say that. Then we also see in the second session, we also saw that electric circuits. What are the different components on the electric circuits, right? Like button or key, we can say switch, right? All same names, same things we can say, right? So we have seen those things. Then we also talked about the different components that bulb is there. Then we have sail. Sail also have two different types. That is either it could be positive, sorry, primary or secondary. Primary cell means what? That smaller cell which we do use in our clocks, right? And secondary cell means the batteries, big batteries which are used with the inverters or in vehicles, right? We know those things. So we have already seen that. Then the main important point we saw about is that resistance. Resistance is what is the Ohm's law. Ohm was the scientist and he gave us very important formula, that is V is equal to IR. Because of that, we were able to calculate the current in the circuit using the resistance as well as the batteries EMF, we can say. So we calculated that part too. Then we also saw what is the electric bulb. What is the material? Is anybody remember what is the material? I told you carefully that you should remember that material name. That is tungsten, right? Tungsten is there. Then how the primary cell works? What are the different components of that primary cell? What about the secondary cell? There are two different electrodes. We should remember that too, right? So we have seen all these things. Now, in today's lecture, what we are going to do, we are going to talk about the electric current a little bit more, right? So we already have seen the current, that is current is equal to V by R, that, right? So today we are going to see what is the formula for current and how actually the current flows, right? Then main important point we are going to talk about is the conductors and insulators, right? So conductors, and what are the conductors and insulators? Obviously, in the previous session we had discussed about there are wires, big cables on the outside road, we can say, which are actually bringing the light from power station to us. Very simple, right? So those cables are obviously should be conductor. Why conductor? Because they wanted to carry the current, right? So can we touch them? Obviously we should never touch them because those are high voltage current carrying wires, right? So obviously they will give us the electric shock, so we should not touch them, obviously, right? What about the wires inside our home? Can we touch them? Still, again, that is not safe, right? We cannot touch those wires. But you must have seen the wireman or electrician who easily touch those wires. So why they can easily touch those wires and not which are outside? Right? Because the wires inside our house has some coating on it. That is called as plastic coating. You must have observed it is a black colored or red colored. That coating is actually insulators. Insulator means what? It will stop current from flowing, right? So normally, if you touch that, generally, you should not get shock. But obviously, don't ever try to do that. Obviously, because that could be risky. If there is some breakage or there is a leak in the current, we can say that could be risky, obviously. But that plastic wire is plastic coating, we can say, is actually going to stop us from getting shock. Okay, so these are conductors and insulators, and we can say obviously insulator do not conduct the any current, but are they useless? Obviously not, right? We saw that the wire has the coating, that's why we are not getting shock. If everything was conductor, then everywhere we would have got shock, right? Even consider the air, right? Air, tell me, air is conductor or insulator? Can air conduct the electricity? Obviously not. If air could have conducted the electricity, then it would have been very difficult for humans to live or any living object to live, because if the air could conduct the electricity, we will get shock everywhere, right? So that's doesn't make any sense. So obviously air is the insulator. Remember that part. Now let's start our chapter. We'll start with the small video on conductors and insulators like this.
Material that allows the flow of negatively charged electrons in one or more directions, which results in electric current. An electrical insulator is a material in which the electrons do not flow freely. What we will do in this video is take a look at some different objects. We have some metals, some plastics, a Sharpie, how about a pickle, and some water. We will hook it up to some electricity and see if it is a conductor or an insulator.
Right, so what we can see here actually is that the person has created some circuit there. Bulb, I can see the bulb there, and wire, obviously something like that, and it is connected to we can say these are our normal connections we can do. Here we can do some connections using those wires, and he is now going to connect the different objects in those two clips, we can say, right? Those are clips, right? And between those clips he is going to connect some objects, and whether those are conductor and insulator. Who will decide it? If the current flows, obviously it is conductor. Who will decide whether current is flowing or not? This bulb, right? Bulb is going to decide, right? If the bulb glows, obviously current is flowing. If bulb does not glow, not flowing, right? So let's check out which objects are insulator and
up first we have copper. Hook it up, and yes, it's a conductor,
right? So first of all, first one is copper, and we can observe the light glows there, so it is a conductor.
How about this piece of plastic? Flip the switch.
Right, so we connected the plastic. Yes, so tell me whether plastic will allow the current or not. Right, obviously it is an insulator, so it should
nothing happens.
Right, so no bulb flows there.
It is going to be an insulator. Now we move on to another piece of metal. It's aluminum. Flip the switch, and yes, it is a conductor. Now, how about some wood? Hook it up. Flip the switch.
Right, so try to guess whether those are insulators or conductors.
Switch. Nothing happens. So it is an insulator. After the block of wood, let's try this. How about we try a Sharpie? It's plastic. It's hooked up. We go to the switch, and nothing happens. So it is an insulator. How about this? Let's try some water. I've got two nails hooked in. I flip the switch. Nothing happens. Well,
right, so here we can see that water is not letting the current pass through it. Right? How you connected the water? You just put the two nails on that clips and put those nails in the water. So obviously, if water would have been conductor, it should have conduct that electricity. But remember, pure water is the non-conductor. But normally, whenever we are using the water, mostly those are salted. There is some salt in that water too, right? So if you have used some heater, that portable heater, right? If you put that heater into your water or bucket, we can say, that will generate the current. And again, remember, don't try to put your hand in that water, because though water is non-conductor, but remember, it is the pure water which is non-conductor, right? Here, our normal water may not be pure. It must contain some, we can say, salt material there, right? Which can conduct the electricity. So that will give you the electric shock. Okay.
Let's modify the water slightly. Let's add some salt. As I add the salt, I pour it in. I go back to the switch. What do you think? Is it going to change? I hit the switch, and yes, it is now a conductor. The salt allows the electrons to move freely. Next, let's try this screwdriver. The reason why I use this, I have plastic on one end, metal on the other. I flip the switch, nothing happens. But now, if I move it to where it is touching metal only, it's now a conductor. So the plastic helps insulate it. How about this? How about the pickle? It has a lot of salt in it. Well, I don't know about that. I plug it in.
Right, so pickle is there. Let's see whether it is insulator.
It smokes
Conductor.
a lot. It glows, but I would consider it an insulator.
Right, so it is glowing, right? There is heat generated, actually, we can say. So even for the insulators, if there is heat generated, it could get damaged. This is the same thing. If this pickle is getting damaged.
How about celery? It kind of tastes salty. Maybe it has enough salt in there. I plug it in and, well, you can see for yourself. Nothing really happens. Well, it does start smoking a little bit. So let's see what happens with the celery with 110 volts going through it. Smoking, but it is an insulator. It's kind of cool looking though. Next, how about the apple? It's kind of a dud. Well, not really. It's an insulator. So if you need to insulate, an apple is your object. So I hope that helps. If you'd like.
Right. So these are the different materials you can see, which are conductor or insulators. Okay. Chalo. Right. So in today's session, what we are going to cover? We are going to cover first electric currents and conductor insulators. We have just watched one very small and informative video on the conductors and insulators. The materials which are conductors obviously will let the current pass through it, and insulators will not. Right. So first of all, let's see what is electric current. So electric current, can I say it is the flow of electrons? That's right. Electrons flow from where to where? It is from negative terminal to positive terminal, that we know, right? But also I had mentioned this in the previous session also, that if the electrons flow from negative terminal of this our normal dry cell to positive terminal, current's direction should be opposite. Right? Remember this part very carefully. Current's direction should be from positive terminal to negative terminal. So for example, consider now we also know how to draw the circuit, right? Simple circuit. Let's try to draw that. This is, I know this is the representation of battery, right? So this same cell, I can represent it by this way. The bigger line shows the positive terminal. The smaller line is going to show negative terminal. Now what I'm going to do here, let's connect one bulb or something here. So that bulb will glow and we can see the electrons are moving from here to here, right? What about the current? Current's direction, as I said, it should be opposite. So it should be, current should flow from positive terminal to negative terminal like this. Okay, so remember this part. Then now current, as we said, current is the flow of charge, right? So we have to prepare one relationship between charge, current, and time. Right? Just charge is denoted by what? Q. Right? Whether it is electron or positive charge doesn't matter. We can denote it by small q, right? Or if it is electron, we can denote the charge by E also, right? But just stay on the basics right now. So we will denote the charge on by the q. Now the electrons, that charge is flowing through the conductor. It cannot flow through the insulators that we know now, right? Q, that q is flowing a lot of charge, many charge. Not only one electron is flowing. We have seen that in the first lecture. First, only one electron is not going to give you a lot of current, right? Very small. That is a very small charge. So many electrons are needed. Many charge are needed. So that will flow like this, right? So now the current, now we know that is the flow of charge. Let's denote the charge by Q. What about the current? I can denote the current by I. I can denote the time by small t. Okay. So I just want the one relationship between these three. So I can say charge, or we can say current, is the amount of charge flowing through the particular time, or unit time. We can say unit time means what? 1 second time. So particular, how much charge is flowing through, let's say 1 second, will be called as current. What are the units? We know the unit for charge is coulomb. and 40 second. So I can say unit of current is coulomb per second, or another unit we already know that it is ampere, right? So current unit could be ampere or it could be coulomb per second. Okay. So this is the basic formula for the Coulomb current, we can say. Now let's solve one example on this formula. We know the formula I is equal to Q by T. Also, we have seen one formula for I in the previous question using the Ohm's law, V by R. We did some calculations on this, right? The battery's voltage is given and resistance is given. We can calculate the current. This is the second formula. Second formula means actually this is a basic formula, we can say. So before Ohm's law, we can use this formula because current, we call current is what? Flow of charge. So it is a bit dependent on charge, obviously. So whenever we are even using the Ohm's law, there is also the charge. Okay, remember that part. Then now tell me, if charge flowing, consider if charge flowing is 100 coulomb, let's take it 100 coulomb, and in time, let's say 5 minutes, and they will ask you to calculate current. How to calculate current? Right? Remember, charge could be shown by capital Q or small q, doesn't matter. Right? So can I say I is equal to what? Q by T, or 100 upon, now remember 5 minutes, minutes is not our SI unit. We have to convert that unit into the seconds. So 5 minutes means how many seconds? Can anybody guess? It's 5 into 10 raised to, not 10 raised to, 5 into 60. 1 minute means 60 seconds. So 5 minutes means 5 into 60 seconds. Let's say 300, right? So let's say 300 seconds. So it's substitute here 300. So how much current is flowing here? 1 by 3 coulomb. Okay. 1 by 3, not coulomb. What is the unit of current? Not coulomb, right? It is ampere. Simple. Now tell me one more. Let's solve one more question. If question says if 10 raised to, let's say 20, 10 raised to 20 electrons, 10 raised to 20 electrons are flowing through the conductor, let's say in time t is equal to 20 seconds. Second, directly the second unit is given. In the previous question, I gave you the unit minutes, then we have to convert that unit to 300 seconds. Right now, the unit is second, and second is our SI unit, so we don't have to worry about that. So 10 raised to 20 electrons are there, and we want to calculate the current. How to calculate? So first of all, I will need to find out how much charge is there, total charge. If 10 raised to 20 electrons are there, first of all, I will need to find out how many charge is on the one electron. So yes, can anybody recall how much is the charge on one electron? It is 1.6 into 10 raised to minus 19 coulomb. That's good. Negative sign is there. Obviously, there is a negative sign for electron because electron has negative charge. But for the understanding purpose, or we can say calculation now, just ignore that. We need the current value of the current, right? We don't need the negative sign. So if one electron has this much of charge, let's calculate how many 10 raised to 20 electrons are there. So what I have to do? Multiply this by 10 raised to 20, 1.6 into 10 raised to minus 19 coulomb. What I will get the answer? We know that 10 raised to 20 and 10 raised to minus 19. What we have to do? Add the powers. So 20 plus minus 19. How much? 10 raised to 1. That's right. So 10 raised to 1 into 1.6. Can I say this is 16? So total charge flowing in 20 seconds is how much? 16 coulomb. Right? So let's find out the current now. Chalo, try this one fast. You got the Q as well as time, and find this out. Right, so charge is how much? 16. Time is how much? 20. So if I do this calculation, I will get 4 by 5 ampere. So current will be 4 by 5 ampere. Okay, so this is how you can solve this type of question, they will either give you charge or they will give you the number of electrons flowing. Or sometimes, now let's take one more question. Let's see if you could do this question. Right. So consider current is given. Now the current is given, let's say 2 ampere is current given, and it is flowing through any conductor in, let's say, 10 seconds. Now carefully listen to the question. Question says, how many electrons are flowing? How many electrons are flowing through the conductor in 10 seconds, right? So how to calculate electrons? There is no formula for electrons and current. We know the one formula, which is charge and current, which is the relation between charge and current. So let's try that formula. I is equal to what? Q by T. Can I directly say Q is equal to IT? That's good. So 2 ampere into 10 seconds is how much? 20 coulomb. So total charge is 20 coulomb. So how many electrons? One electron will give you how much? 1.6 into 10 raised to minus 19. Right? Let me write it here. One electron. So I can say now just reverse this one, right? So here I have written one electron means 1.6 into 10 raised to minus 19. So 10 raised to 20 means how many coulomb charge? So let's write it in reverse way. 1 coulomb, sorry, not 1 coulomb, 1.6 into 10 raised to minus 19 coulomb means 1 electron, right? So 20 coulomb means how many electrons? How to do this calculations? For that, what I'm going to do, I will just 21.6 into 10 raised to minus 19. Right? So let's try to calculate this. Let me do this calculation here. So I'll write it here, 21.6 into 10 raised to minus 19. This becomes, now this 10 raised to minus 19 is in the denominator, right? Remember, if you want to take it upward in the numerator, what you have to do? 20 into 10 raised to plus 19. Remember, this is simple basic things we can say, right? Divided by 1.6. I can write this as 5 by 4 into 10 raised to 19. And I'm just switching this 1 point here, that becomes 10 raised to minus 1. So just a little bit of modification. How that 1.6 I can write it as 16 into 10 raised to minus 1. Right? So 10 raised to minus 1 will be like this. So I can say this is approximately 5 by 4, or I can say 1.25 into 10 raised to 20. So these meaning number of electrons, right? We will get, right? So this is the basic relation between, we can say, current, charge, and time. Those different things are there. Okay, so this topic is important. This formula is important, right? This was the formula we have seen in the previous session, that is Ohm's law formula. And here we saw this one important formula, that is I is equal to Q by T. And we tried many examples, different types of examples, right? So very simple. What we should know about this one? What is the charge? What is the unit of charge? What is the unit of T? What is the unit of current? And we should be able to easily get all the answers, right? And one more thing they will ask, how many electrons are flowing through it? How to calculate electrons? We also saw that, right? So there are 3 different types of problems we saw here. You should be able to remember this. Okay. Now let's move to the next part. Now, in the previous session, we have already studied about the resistances in series and resistances in parallel. Let's have a quick look there. So this was the diagram, if you do remember, in the resistance in series, right? And in resistances in parallel, this was the diagram. Okay, here I asked you to remember 2 things. In the first, in series case, current remains same. I told you, current remains same. And who changes? Potential changes. Remember this part. In parallel, what happens? Potential remains same. Potential remains same. And who changes? current changes. Simple. Here we got the value that if the potential is changing, V is equal to what? V1 plus V2 plus V3. Here what I can say, I is equal to I1 plus I2 plus I3. Finally, I got the relation for R equivalent. This is the important thing we want to calculate. That is R1 plus R2 plus R3. Here I got the relation 1 upon R equivalent is equal to what? 1 upon R1 plus 1 upon R2 plus 1 upon R3. Here, remember, after you solve all the problem, total problem, what you have to do? You have to inverse that part too, right? So these are the basic things you should remember in series and parallel. Now also we also consider if these resistances are 5 ohm, 5 ohm, 5 ohm, right? What are R equivalent we got? I can draw one simple diagram, right? So R equivalent is how much? 5, 5, 5 will be 15 ohm. Directly add those. Here also we solved one question. Okay, there's no battery there, right? So let me draw one battery here. Right, to current to flow, obviously we know battery should be there, right? So this is I. Here there is V1 between these 2 points, right? Here V2 is there and V3 is there. Current is going to remain same, we know that. This is V. V is going to remain same now, and the current is going to get divided, right? So what I will get from here, let's replace this point. We have taken the example that 6 ohm, 6 ohm, 6 ohm, if you do remember, and you solve this, or we solve all this equation, and I got the value as 4 ohm. We have completed this question, and if you want, you can try substituting the values in R1, R2, R3. You can easily get the value as 4 ohm. So remember one more thing here, the R equivalent increases. Right, this is the thing I want you to write. Therefore, I repeated this topic here. R equivalent increases. Here, remember R equivalent decreases. Then it divides the potential. It divides the potential and it divides the current. So these are the different points you should remember: the resistance in series and resistance in parallel, right? So I think you will be able to solve the questions on these two right now. Okay. So let's do one thing. I will give you one question in each of those. Try to solve this one. Right. So R1 is 2 ohm, R2 is, let's say, 3 ohm, and R3 is equal to 5 ohm. Calculate the R equivalent. Very simple, right? Here also, let's take the same value for series and parallel. Let's see what will happen. Okay. So what is the R equivalent here? R equivalent will be just addition of these two, that is 10 ohm. Try to calculate this one. Now obviously this becomes a little bit of difficult. Your denominator is not same. So if the denominator is not same, obviously you have to make it same. Right? So take the LCM of denominator and try to solve this one. Right. So how much is the answer? So I think we got 1 R equivalent is equal to, check your answer, it is 31 upon 30. 15 plus 10, 25 plus 6, 30, right? So I can say R equivalent becomes 30 upon 31. This is the answer. Okay. So this is, we can say, the cases of resistances in series, resistances in parallel. Right? This concept is very important, so you should remember this one. Now, let's move to the next point. Series combination. of the lamps. Now we are talking. Now we know about series combinations of the resistances, right? So we already seen that. And we want the series lamps in parallel as well. Okay, series as well as parallel. Now, where we have seen these types of things. Now, consider if you want to connect the two lamps in series, right? Means what? You will only use one wire. One battery is there. Only one wire is there, and these are the two lamps you connected, right? And in second case, when we say parallel combination, we what we can do, we use the two wires. Means diagram will look something like this. This is the battery. Consider this is the one wire. We connect the one bulb here, right? Then the same thing, attach the one wire here and connect the another bulb, right? Like this. So this will be the parallel combination. Okay. So which combination we should use, whether we should use the series combination or parallel combination to connect the bulbs. Even in our house, we know there is wiring, right? Obviously wiring. So one wire is going to all the instrument, whether it could be TV, it could be fridge, it could be bulb or tube, etc., etc., etc. So should we connect all those in parallel or series? So let's see what is going to happen, right? In series and parallel things, right? Now seal is there, then we already know that current is going to go into this one, right? Current is going to remain same, and two volts will read something like that. Now consider what happens here. Consider this is the there we are. I also connect the third bulb here. Now assume that due to some fault, the one part of this wire, this part, consider this part, it breaks, right? This part breaks. What will happen? Current is starting from the battery, right? But it cannot find a space here to go. Now there is break. When the circuit is break means what? We know current is not flowing. So even only this part of the wire is broken. What will happen? Total current will stop, right? So all the bulbs will stop glowing. So if the small part at one point is going to break, the whole system will fail, we can say. So instead of that, what we can do, use the parallel bulb. So what happens? Consider there are many bulbs like this, right? And let's say one of the wire breaks now. Let's say this wire breaks. What will happen? The current cannot flow here. So obviously this bulb will not glow. Which one? This one. This will stop glowing. But current have the direction or the circuit to flow from here. It will also flow here. It will also flow here and come back to circuit. So main idea of the current or circuit, we can say, if the current starts from the positive terminal, it should end up to the negative terminal. This is the basic idea. In the previous case, what we have seen, if the wire breaks at one point, the circuit is broken. Circuit broken means what? Current will not flow at all. If the current is not flowing, bulb will not glow. Simple. But in second case, in parallel combination, what we can see here, if the circuit is broken at one part, current is still flowing through all the other bulbs. So now tell me, which combination will be useful? Which combination we should use, right? Obviously, parallel combination we should use, right? So you must have observed in festival season, right? Let's say if there is a big season, so like Ganpati, Diwali, Christmas, Eid, right? So for all these season festivals, we do use the lightings, right? Lightings around our home, etc. Those are, we can say, very big wire of lightings, right? Small LED light, we can say, right? So those lightings are actually not in a straight line. They do look like they are straight line, right? So many bulbs are there here. So many bulbs are there. They do look like connected in series, but if you observe that wiring, there are 2-3 wirings are going inside, coming back. If you do observe that, if you do have some wiring left, right, you must have it in the house, right? So what I can say, consider I zoom this part. Let's zoom this part, right? So bulb will look something like this. So there is not only two wire, there are more than 2-4 wiring are going like this. So this bulb is not actually in series. These bulbs are connected in parallel. So even though if one bulb fails, right, others are glowing. This is the concept behind the parallel combination and series combination. This is the same thing as our, we can say, series resistance or parallel resistance. Same thing we can also use here. Okay. So always remember, even in our home also, we can consider that all the instruments are connected in parallel case instead of series. Okay. Now, so let's move to the next point. Now, conductor and insulators, we have already seen one video on the conductor and insulator. There you have seen which material is insulator, which material is conductor, right? So you have to do one thing, list out all the materials. We'll see what are the different examples of conductors as well as insulators. Try to list them out. So in exam, they could ask you which of the following is conductor or which of the following is insulator, right? You should be able to tell them, right? Now here I can see the wires are there, different colors of wires, green, black, brown, blue wire is also there, right? And inside that, these are the copper wires. Or you can also use the different material, aluminum wire or silver wire, but obviously we will not use the silver wire, right? Why? Because silver is very costly. Even the gold is the conductor, but that doesn't mean that we are going to use gold to conduct our electricity, right? That's not practical. That will be very costly to just put the wire of the gold, right? Impossible, right? So for this wire, I can also see the conductor. This copper part is the conductor that is actually going to carry your electrons throughout the circuit, even throughout your whole network of the light and etc. in your home. Many wirings are there, right? We know that part. And these are the plastic material. These are actually insulators, we can say. So even though the current is flowing, as I said, if your electrician hold this part, plastic part, he is not going to get shocked, right? But still, as I said, that we should never try this. There may be leakage, or if insulator is, let's say insulator is broke somewhere, obviously the current will leak and we will get shocked. So never try to do that, right? Okay. So again, I can say this copper part is going to conduct the electrons and insulator is going to stop us from getting electrical shock. Okay. So let's see how many different types of materials are there. As you can see, silver, as I said, silver, gold, both are conductors, but obviously we are not going to use them in our wiring. Copper, is the one which we are using actually in the wiring. So copper is a good conductor. It is going to conduct electricity, obviously. Then steel, right? Steel means we mostly in kitchen we do use the steels, cans or etc. Right? Steel tiffin is there, but those are not used for to conduct the electricity. And our seawater, right? We have seen in that video that pure water is not the conductor; it is the insulator. Pure water is not letting the electricity to flow, but you have seen in that video the person added the salt in that. Once he added the salt, what happened? Electricity got conducted. Bulb was glowing again, right? So this is the thing about the water. So salted water can conduct the electricity, and normal pure water will not conduct. So again, I will recommend that never try this. Never try to put your hand in the water which has the electric current in that, right? Like a heater, we can say electrical heater is there, which is inside the water. Never try to check the temperature of the water, because if the water is salted, obviously you will get the electric shock in that case, right? So these are some examples of conductors. Then let's talk about the insulators, right? So in the previous session, we have seen that there are very big towers are there, right? So those towers actually what they do, these are wires. You can see these wires are going outside, right? These wires are actually going to carry the current. So tell me, is that current is low voltage or high voltage? I told you this point, and you should remember this point, right? Yes, that's a high voltage line. So this current, these wires are actually carrying the current which are very high voltage current, right? And even though this is the wire which are carrying current, we have to separate these two things. Now this is the wire, right? Even you can see there are two wires. I can see even in those two wires there is a small part, right? That is actually also insulator. This part you can see in that tower, this big part is also insulator. Why we have to use the insulator there? Now consider for these two wires. These two wires are what? Those are conductors. If they meet each other, what will happen? Right? There will be sparking, right? It is called as short circuiting. If the two wires which are carrying current close to each other, right, comes close to each other in contact, we can say. So actually what is happening, consider this first wire, right? First wire is carrying current from the power station to our home, and this second wire is again carrying current to the power station. So if those got connected like this, what will happen? This two wires will get connected here, and current will come here and left from here, right? It is called a short circuit. Here a lot of heat is generated, and there will be a sparks, we can say, and the danger of the fire, right? So what we have to do, even those these two wires are close, or we can say these wires are close, we have to separate them properly using the insulator part. So these are the insulators. This very big part is there, right, which are connected between these two wires or all those tower part, right? So this is going to stop the current to flow from those two wires, right? So, what are the different objects which do act as the insulators? We have already seen that in the video. Yes. Anybody remember the which are the insulators? First, he have tried the that person have tried the plastic part, right? Plastic was not carrying the current, right? Bulb didn't glow, so we can say plastic is insulated. Which are the other ones? Wood. Yes, wood is the obviously, wood is also the insulator. Pure water is insulator. Pickle we have seen. Pickle is insulator, but it started. There was spark. Why there was spark? As I said, if the current is flowing here, then now obviously we can get some spark in there. Okay. If the heat is generated, a lot of heat is generated, there will be spark. Right? So insulator should also be, we cannot use any insulator there. Obviously insulator should have high melting point, we can say, right? High melting point, because if the current passes through it, heat will be generated, and if heat generate, then there is a possibility of fire. To avoid that, insulator should also have some properties to be used as an insulator like this. Okay. So now let's see. Rubber, right? Our eraser, we can say, our eraser is insulator. Then glass. They're not talking about the water here. Pure water, we already know pure water is insulator, but the glass is also insulator. Then you can take the example of oil or wood or diamond. Here they have mentioned the dry wood. Yes, can anybody guess why they are saying that it is the dry wood? Because if it is not dry, there is a moisture in there or water particles are in there, and we know if the water particles and also salt, they will also have some salt, then it will conduct the electricity, right? So we will only need the dry wood. We cannot take the our moisture wood, right? So only dry wood can be insulated. So in this case, can you use the wood as the insulator here? No, not obviously, because in rainy season, what will happen? The water will get generated in the wood, and that will not act as the insulator, right? So this we can use the plastic or high quality plastic, we can say, or ebonite materials are there. So we can use those material as the insulators. Even consider in our home also, you must see the lot of insulator materials, right? As we have already discussed, that wire also has the coating which is insulator, plastic coating. That plastic coating is also not a very cheap material. It's a very high quality material. It should not, do try that, it should not break easily. Okay. So these are about the insulators. Okay, so what we have studied, first of all, we have studied the current, right? What about the current? Current is what? We can say current or charge. It is dependent on charge. How much charge is flowing through the conductor? So how much charge is flowing through the conductor? We can say it depends on the time there, right? And Q by T is our basic formula for current. Simple. Now, then we also studied how many electrons are flowing if some amount of charge is to be flow from that conductor, right? So we also got one very important formula at the start, that I is equal to, or Q is equal to I into T, or I can say I is equal to Q upon T. That was the initial formula. Then we also talked about the resistance in series and resistance in parallel. We also solved some questions on that. Then the important concept in this one is conductor insulator. We watched one video on that, which particles, which objects are conductors, which are insulators, etc. Right. So these are the all three part of this chapter. This session also and this chapter also. Today we will end this chapter. So first of all, so let's see how some questions on this one. So how many concepts we have understood now. So first question says state true or false, right? Let's see. The plastic coating over the electric current carrying wire works as insulator. Is that true? That's right, right? Insulator, it is the insulator. The inside part is the, we can say it is the copper part. It is not the insulator, it is the conductor. Second, when the electric circuits are open, current flows through it. Open means what? It is broken. If it is broken, will current flow through it or not? Obviously, current will not flow through it. So can I say this is false? That's right. This one is false. Let's move to the next question now. So what they are saying, find a total resistance and current flowing through the following circuit, right? So first of all, let's check whether the resistances are connected in series or parallel, right? As I can see, those are connected in parallel. What I have to do, I have to draw the equivalent diagram, which will give me the same amount of resistance, but instead of two resistance, I have to just consider or join, we can say, only one resistance, which I can call it as R equivalent, right? And when we connect the resistances in parallel, what we have to do, we have to use one formula. R equivalent is equal to 1 upon R1 plus 1 upon R2, right? So let's try this one. Start solving this equation and find out the R equivalent. So they are asking us to find the total resistance meant equivalent resistance, we can say. And current, we already know current, how to find. We will see that too, right? So first of all, let's try and find out the equivalent resistance, right? Sure. So let's put the values. I'm solving this. Check your answer whether you are getting the same thing, right? Here, what we have to do, denominator should be equal, right? So how to do that? 6, we can say, let's make the denominator same. So to make this as 6, what I can do, just multiply and divide it by 2. So this will become 6. And in the numerator, it will become 2, right? Or second method, what you can do, there are two types how to solve this question. You can either multiply and divide by 2, so you'll get the same denominator, or you can just cross multiply it. Cross multiply means what, right? Let me write it here. So 1 by 6 is equal to plus 1 by 3, right? What I can do, cross multiply it means, let's take this 3 here, and let's take 6 here. So this will become 3 plus 6. In the denominator, we have to put 6 into 3. Right? Let's see whether both are giving us the same equation. This denominator will become 6. 1 plus 2, right? 1 plus 2 will give me 3 by 6, and 3 by 6 nothing but 1 up. Let's try this one. 3 plus 6 is 9 by 18. 9 by 18, now 9 2s are 18, right? So can I say it is 1 half, right? So use any method to solve this one. Either you can cross multiply it or make the denominator same. So I got 1 upon R equivalent as 1 half. So R equivalent will become how much? 2, right? So what I can say, instead of this 2 resistances, I can just connect one resistance here of 2 ohm. Battery is 3 volt. Now try to solve this question. We got the total resistance. They are also asking us to find out current. So how much current is flowing through it? How to find out that? Ohm's law, we have studied that in the previous session, right? So E is equal to I into R, or I is equal to V by R. Substitute the values. V is given, that is how much? 3 volt. Ohm resistance is 2 ohm. What is the unit? Ampere. So I got the total resistance as well as current flowing through this circuit. Okay, so this is the important question for us. Series combinations or this parallel combination. Now just modify this question a little bit. Instead of connecting this in parallel, what happened if I connect these two resistances in series? Right? Can anybody tell me what will be the R equivalent? For series, we know that we just add these two equations, R1 plus R2, right? So series is very easy. Just add these two. It will become 9 ohm. And what about the current? Current will be V upon I. Or I can say 3 by 9 is equal to how much? 1 by 3 ampere. So if you connect these two in parallel, you are getting 3 by 2 ampere. If you connect in the series, you are going to get 1 by 3 ampere. Right? So accordingly, you should first observe whether it is in series or in parallel. Accordingly, you can solve this type of questions. Okay. Now, let's move to the next question. So two resistances, 6 ohm and 3 ohm, are in parallel and connected across 3 volt cell. If you observe clearly, this is the same 6 ohm and 3 ohm connected in parallel, and we got the 3 volt battery. Same thing is there. But they're asking how much heat will be produced. Now, we don't have the heat's formula here, but let's write down one formula for heat also. I can say heat is equal to V I into T. This is the formula. V is how much? 3 volt. We also calculated the I in the previous problem. Problem is same. Resistances are same. Connected in parallel across the same battery. So how much current I got? 3 by 2, right? So I can take the value from the previous 3 by 2. And the T is given as 10 seconds. Right? So obviously, if this question appear in the exam, you have to draw a diagram, right? That the previous diagram. And using that diagram, you have to first of all calculate the current and etc. all those things, and then only you can get the current is 3 by 2. You cannot directly write 3 by 2, right? So this is 3 ohm, so 3 volt, 6 ohm, 3 ohm. Calculate all those things. Current you will calculate. First of all, you will calculate R equivalent, right? R equivalent was 2 ohm. We calculated that in the previous case from using the Ohm's law, that is V is equal to IR. Calculate I is equal to 3 by 2. And the T is given here. So heat produced in that resistance, the formula is very simple. V is equal, H is equal to VIT. So can I say 3 into 3 by 2 into 10? Simple. So let's do this small calculation. That will be how much? 9 by 2 into 10, or 9 into 5 I can say, or 45. And unit of heat is given as joule or calorie, we say, right? But SI unit is joule. So our main unit is joule, so we are going to use joule here. Okay. So this is another question, you can solve it. Just if they ask the heat, what is the formula? We got the new formula, so note it down somewhere. Right. So if this question appears in the exam, we will be able to easily solve this, right? Very simple formula, just equate H is equal to VIT, and other processes are normal. We already know how to calculate R equivalent. We know how to calculate current and etc. Simple. Now let's move to the next question. Which of the following is not a conductor? Copper, mica. Okay, so mica is double. So let me replace this mica word, right, by gold. Right, we have seen the conductors and insulators, right? So we already know what are the different conductors. So we don't know about the mica, right? But they are asking which is not the conductor. What we know, copper is conductor. Yes. What about silver? Conductor. Gold? Conductor. So who is remaining? Mica. So obviously mica could not be a conductor. So mica, remember, it is the insulator. So in our list, add one more name, that is mica. Mica is a material which is a little bit of like of we can say plastic material, and most probably it's come into the black color, and it is most of the times used as insulators, right? So remember, mica is not the conductor. In your list, add that mica, right? Okay. Others, copper, silver, gold, those are our conductors. Next. Overhead cables need not to be insulated. Overhead cable means the cables which are flowing outside, taking sorry, not flowing, which are outside on the poles and carrying the electricity, right? So those are not insulated. Those are only just aluminum wire or copper wire. Those are right. No plastic coating is there in our home. We already know in our home there is a plastic coating, but those don't have any coating. You can see those wires from with dyes, right? Simple. So why those are not insulated? Right? So let's find out the reason. Options are, first option says air is a bad conductor of electricity. Have we studied that? Is air a bad conductor? Yes, air is a bad conductor. So this could be option, right? Correct option. Second, air is a bad. Okay, again there is one mistake here. Let's say this is good. Let's replace this by good. So air is a good conductor of electricity. Obviously, it is not good. So this option is wrong. Current does not flow through these wires. Obviously, current flows through those wires. This is the purpose of those wires, right? So this is also wrong. And this is none of this. Obviously, this is our correct option, that air is a bad conductor of electricity. So what I can say, that as air is in contact with them, so air does not carry the electricity, so we are not going to get shocked. Obviously, those wires are not at our height; those are very high, so we have to jump to touch those wires, and obviously, we're not going to do that. We know that that's not safe, right? So they don't need the insulation there, as air is not going to conduct electricity. Okay. So these are the different questions we have seen, and we have completed our second chapter here, that is electricity and circuits, right? So what we have studied the charges, that is protons, neutrons, electrons, what are the masses, what are the charges on them. We also have studied about if the charges are flowing, current will also flow, and who is responsible for that current to flow. And our cells, we can say, cells could be what? It could be primary cell, like our small cell. It could be secondary cell, means battery, which we use in the vehicles. Or the biggest source of the light is what? Electricity is what? It is our uh, power station, right? Power station, electricity is generated, and we got that electricity through the cables, right? So we also studied that. Then we know about the different elements in the circuit, that is button. Then we also know about the key, switch, button are the same thing, right? Cell we know. Then we know the bulb. Then yes, how the cell works, we know that part. And we know the resistances. Resistances is an important part, right? Resistances in series, resistances in parallel. Then we have also seen the problems of them. Then today we also seen that current's formula, current is equal to Q by T. One formula we already know, that Ohm's law, V is equal to IR, right? We also can calculate current there. Another formula, the basic formula we can say is I is equal to Q upon T, that is charge upon time, we can say. Then we also studied about the conductors and insulators, right? So this completes our whole chapter. So do one thing, study all this chapter. And if you do have any questions or queries, do put those queries in forum. Okay. So we'll start the next chapter in the next session. So today we'll stop here. So thank you very much. Have a nice day.